All right, hey guys, so we are moving on to section 8.5 here. So we're still talking about quadrilaterals, but up until this point, every special type of quadrilateral we've talked about has also been a parallelogram. Rectangles, rhombuses, squares, they've all been a parallelogram up to this point. Today we're going to talk about these other two types of quadrilaterals, excuse me, that aren't parallelograms. All right, so our first one is a trapezoid. So here are some definitions. We do have a lot of definition and theorems right at the beginning, so go ahead and pause the video when you need time to write everything down in your notes or to take it all in or to practice a problem. Like, go ahead and make sure you guys pause that video and then come back when you're ready. But a trapezoid is a quadrilateral with exactly one pair of parallel sides. This right here is what makes a trapezoid different from a parallelogram. Rather than having two pairs of parallel sides, it only has one, and we call these the bases. So looking at our picture down here, these right here, they're parallel, and they're called the bases. A trapezoid also has two pairs of base angles. So in this picture, angle A and angle D would be a pair of base angles, and then angle B and angle C would be the second pair. Because they go with the bases, we have two pairs of base angles. And then our last little definition here is the non-parallel sides are called the legs. So this is really just a bunch of vocab. It doesn't tell us much. We'll use this definition right here, this top one, for our first example later on. But other than that, really just make sure you guys understand this picture, what everything's called, so that theorems will make more sense. Because for the most part in this class, we're going to focus on isosceles trapezoids. Let me get this where you can see it. We're going to focus mostly on isosceles trapezoids, which, just like an isosceles triangle, means we have two of the legs that are congruent. So isosceles hasn't really changed, still have two congruent sides, but for a trapezoid, it's specifically going to be the legs. So then our theorems that go with this are right here. So again, pause the video if you need time to write these down. Excuse me. Our base angle theorem. If a trapezoid is isosceles, then each pair of base angles is congruent. So we talked about the base angles on that first definition slide, but now an isosceles triangle, or trapezoid, sorry, they're congruent. And then we also have the converse of that, so kind of just flipping our logic around. If a trapezoid has a pair of congruent base angles, then it is isosceles trapezoid. So it's kind of flipping the logic around, but using the same facts. And then our diagonals theorem, a trapezoid is isosceles if and only if its diagonals are congruent. So we'll use this fact a lot as well. So diagonals are congruent. Each pair of base angles is congruent. And this is why we talk about isosceles trapezoids a lot more, because it gives us more to work with. So then, some more definitions here, then we'll get on to examples. Last slide. Last little bit here we got to talk about is the midsegment of a trapezoid. So we have talked about midsegments before, and in a triangle. We've talked about this special segment in triangle back in chapter 5, I believe. And if you just remember that in a triangle, the midsegment connects the midpoints. Well, it's the same idea with the trapezoid. Midsegment of the trapezoid still connects the midpoints of the legs. So right here, MN would be our midsegment. And then our theorem that goes with that right here, the midsegment of a trapezoid is parallel. So that was the same as when we talked about triangles. It was parallel to each base, and the length is 1/2 the sum of the length of the bases. This 1/2 part stayed the same as a triangle, but the sum part is what's different. So basically, this theorem gives us a formula. So if MN is our midsegment, we know that our midsegment equals 1/2 times the sum of the bases. So AB plus DC. And this formula right here, you're going to want to memorize because it's going to come up a lot. In most cases is they give you 2 out of the 3 and ask you to solve for the missing information. So it turns into just like a 2-step problem most of the time. But that's really what you're going to be using with this. So you're going to want to make sure you have this formula written down. So now let's move on to our examples. Our first example here is just a normal trapezoid. We haven't gotten into the isosceles trapezoids yet. So just a normal trapezoid, and they just want us to show it's a trapezoid. And to do that, we're going to have to show that we have one pair of parallel bases and not 2 pairs. All right, so basically we're going to find the slope of all 4 sides and show that RS is parallel to OT and that RO is not parallel to ST. So essentially the easiest way we can go about this will be using that slope formula we know. So m equals y2 minus y1 over x2 minus x1. So using that formula, I want to go ahead and find the slope of RS. Just using that formula, so I can do 4 minus 3 over 2 minus 0. Just do my subtraction here. I would get the slope is 1/2. So let's go ahead and do the same thing down here for OT, because I know just by looking at it, those are going to be my parallel sides. I can do that the slope is 2 minus 0 over 4 minus 0, which is just 2 over 4, which indeed is 1/2. And we know, since these are the same slope, that RS is parallel to OT. So I have my parallel sides now. I have my parallel bases. So then to show, excuse me, that it's just a trapezoid, I have to show that these other 2 legs are not parallel. So let's just keep finding the slope. Slope of RO, I can do 3 minus 0 over 0 minus 0 to get 3 over 0. And in math, we hate this dividing by 0. We can't do it. It's undefined, which tells us our slope is undefined, which hopefully we saw just by looking at the picture because it's a vertical line, which we know back from, I think, chapter 3, vertical lines have an undefined slope. So then comparing that to ST, we can do 4 minus 2 over 2 minus 4 to get 2 over -2 to get -1. Undefined and -1 are indeed not the same thing, so we know the RO is not parallel to ST. So then we showed that we have one set of parallel sides. So then we could say ORST is a trapezoid because it has exactly one pair of parallel sides. And that's the gist of just working with normal trapezoids. Nothing fancy. We're not using isosceles trapezoids quite yet. That's kind of the gist of that. Just using a lot of slope formulas showing that some sides are parallel and the others are not. So if you struggle to follow along with that example, this guided practice example right here will be worked out on Classroom. I'm not going to work it out in this video because I want to focus on isosceles trapezoids today, but you can look at these on Classroom to help you out if you need a little bit more help. So moving on to example 2, isosceles trapezoids. So we have an arch problem here. The stone above the arc in the diagram is an isosceles trapezoid. Find the measure of angle K, the measure of angle M, and the measure of angle J. Well, since we know it's an isosceles trapezoid, we know it has 2 pairs of congruent base angles. I don't know if you guys can see this right here, but this angle L says it's 85 degrees. And we know, well, if L is 85 degrees, angle L is congruent to angle K, so angle K must also equal 85 degrees. Because we know that L and K are base angles, and if it's isosceles, we know the base angles are congruent. And we also know that the other set of base angles will be congruent as well. So to figure out what these are, I'm going to use the fact that all of this added together is going to equal 360 degrees because it's a four-sided shape. So we know that angle J is going to be congruent to angle M. And if I do 360 minus 85 minus 85, I get 190. Which means I have 190 to work with right here. Well, gotta divide that by 2 because they're going to be congruent. And I'll get that angle J and angle M are both 95 degrees. And that's how you can go about finding the rest of the angles. But something I want to point out right here is how we could have used a shortcut. It turns out that in a trapezoid, these angles right here are going to be supplementary. Meaning they add to be 180. And we could check that by doing 85 plus 95 to get us 180 degrees. So I could have just done 180 minus 85 to get my 95 down here. And that would have been a little bit more of a shortcut, but we got the same thing by just taking it from using the 360 and subtracting and dividing by 2. So fun fact, this might give you a little shortcut in the future. The two angles that aren't congruent are going to be supplementary, meaning they add to be 180 degrees. So a little fun fact. Again, so angle L and angle K were 85, angle M and angle J were 95. So then we're going to keep moving on. Now we have an example with the mid-segment. So, example 3, use the mid-segment of a trapezoid. In the diagram, MN is the mid-segment of the trapezoid. So basically, here's our X. We want to figure out what MN is, and that's when this formula is going to come into play. Since MN is my mid-segment, I know it's going to equal 1/2 the sum of the bases, so PQ plus SR. So then plugging in what I know here, well, MN's X, got my 1/2, PQ is 12, plus SR is 28. Well, 12 plus 28 is 40. 1/2 of 40 is 20. So there's the length of my mid-segment. And kind of like I mentioned earlier, they're just going to move this X around. You're going to use this formula every time. It's so important that you guys know this formula for mid-segment because they're just going to bounce this X around and make you solve for it. So it's really important that you guys memorize that and have that written in your notes. So now we're back to the examples where I want you guys to pause it and try it on your own and then come back to the video when you're ready to check your answers. Just go ahead and pause it. Okay, number 3. If EG, so that diagonal right there, equals FH, this other diagonal is in an isosceles trapezoid. Well, yeah, because we know a trapezoid with congruent diagonals is isosceles. And we can abbreviate a little bit there. And that's just using that theorem. That's just knowing those theorems that we said at the beginning and just using that to say, yes, it's isosceles. Like a yes or no question. For number 4, the measure of angle EHEF is 70 and FGH is 110. Is it isosceles? Well, that little shortcut I told you in that one example a little bit ago tells us that these guys are going to be supplementary. So if I do 180 minus 110, I get 70 degrees. Well, if I do the same thing over here and do 180 minus 70, I get 110. So yeah, it is an isosceles trapezoid because it has two pairs of congruent base angles. And again, that's just using those theorems at the beginning and then using that fact that we know they're supplementary. Number 5, just a little bit trickier because you had to draw the picture to start. We have a trapezoid and they tell me angle J and angle M are right angles, meaning they are 90 degrees. And I know that they're going to be on the same side of the trapezoid because they're first and last here. So my picture is going to look something like this. You guys have probably had a different picture and that's okay. As long as it's a sketch and you had 2 right angles in there for J and M, be good to go. And I'm going to fill in the other information I know because JK is 9 and NP, which is the mid segment, is 12. And they want me to find ML. Okay, well there's X. I'm just going to use that formula we said. We said that NP is going to equal 1/2 sum of the bases, JK, plus ML. I'm going to plug in what I know. Well, 12 equals 1/2 9 plus X. And then this is where, got to do a little solving here. To get rid of this 1/2, you're always going to multiply by 2. Multiplying by 2 and multiplying a half, they're opposites of each other, inverses. You're always going to multiply by 2 to get that 24 equals 9 plus X. And then this turns into a basic one-step. Subtract the 9 to get that X equals 15. And that solution process right there that we just did is going to be very, very similar anytime the X is in the parentheses here. So whenever X is in the parentheses here, you're always just going to multiply by 2 on both sides to get rid of that 1/2. And then just to subtract the other side that you know, once you multiply by 2. So hopefully you guys got that written down, so you have a little example of what to do when you have trapezoid problems on your own. Because for the next part of the lesson, we're going to talk about a kite. This is our last type of special quadrilateral we're going to learn in geometry this year. And a kite is a quadrilateral that has 2 pairs of consecutive congruent sides. So this is very different from what we have done already, because everything so far we've had opposite sides being congruent, but now it's the consecutive sides that are congruent. All right, so then our theorems down here that go with a kite is our diagonal theorem. If a quadrilateral is a kite, then the diagonals are perpendicular, meaning they create that 90-degree angle right there. And then for our angles, if a quadrilateral is a kite, then exactly 1 pair of opposite angles are congruent. And it's always going to be the pair that joins the 2 different side lengths. All right, the angles that are going to be congruent is the angle that joins the 2 different side lengths. And that'll come in handy here in our next few examples. So make sure you guys pause that video, get those written down. In your notes, you're going to want a list of all this stuff. So we're almost done. 2 examples to wrap this up, and they're a little bit quicker than the last ones. Applying the kite theorem, find the measure of angle D in the kite shown to the right. Well, just looking at the picture, I know that this is 124 degrees up here. This guy down here is 80 degrees. Well, they aren't congruent. And if it's a kite, I know I have to have 1 pair that's congruent. So angle D has to be congruent to angle F, just based off that last theorem I just read. So then to figure out what those are going to be, I know that all 4 added together are going to equal 360. So I can do 360 minus 124 minus 80 to get 156 degrees left over. And if these are congruent, I can take that 156 and divide it by 2 to get that each angle is going to be 78, meaning the measure of angle D is 78 degrees. And we've done a lot of problems like this in the past, and that's why I went through it a little bit quicker. But that's just using that 360, which I feel like we've done a lot in this lesson so far, and knowing that these are congruent, so dividing by 2. So why don't you guys go ahead and pause the video and try this last example on your own, and then come back when you're ready for the answers. Okay, in a kite, the measure of the angles are 3x, 75, 90, 120. Find the value of x. Well, again, I'm going to use the fact that they all add to be 360. I'm going to do 3x plus 75 plus 90 plus 120 equals 360. I'm going to clean it up a little bit and combine like terms here to get that 3x plus 285 equals 360. Turns into a two-step problem. Subtract the 285 from both sides to get that 3x equals 75. Divide by 3 to get that x equals 25. So first part of the problem is done. Now, what are the measures of the angles that are congruent? Well, I can take this 25 and plug it back in up here for x to get that this guy is 75 degrees. So my 4 angles are 75, 75, 90, 120. Well, 75 is repeated twice, so the 2 congruent angles equals 75 degrees. And that's kind of the gist of that one. Again, we use this fact that they all equal 360 a lot in this lesson, so make sure you guys are still remembering that way back from the beginning of chapter 8. So that wraps up our lesson here. So here is your homework assignment for the night. We have page 540, 7 through 15 odds, and then 19 through 23 odds. That's for both college prep and CP. It'll also be posted on Classroom. But as always, if you guys have any questions, these notes will be posted on Classroom all filled out, as well as you can email me with any questions. So just let me know. Bye.